Okay, so this is homework problem 16.4. And I've pre-written some stuff out here to hopefully save some time. So the question says, calculate the energy levels of the pi network and hexatriene. Alright, make a note here, hexatriene, what the heck's that? Alright, yeah, it's hexa. 1, 2, 3, 4, 5, 6, triene, okay. In hexatriene, using the particle in a box model. PIAB. To calculate the box length, alright, what is box length? Oh yeah, 0 to A. A is the box length. To calculate the box length, assume that the molecule is linear and use the values 135 and 134. For 135 for a double bond, 154, is that right? For a single bond, that's right. What is the wavelength of light required to excite to the first excited state? Okay? So that's the first question. What's the wavelength to go from the first excited state? So we know from page, I think it's 363, is that right? Page 363, that the first excited state is not necessarily n is equal to 2, right? N is equal to 1 is the ground state for a simple system. But for a conjugated system, the number of electrons, right, is, so 1, 2, 3, 4. How many electrons in this system? In the pi system. How many electrons in the pi system? 2, 4, 6. So we've got 6 electrons. 2, 4, 6. And that's as low as you can go. That's the ground state. So n is equal to 3. N is equal to 4 is going to be the first excited state, where one of these guys jumps up here. By the way, that's on page 363, an explanation of that. So what we're going to do then is we're going to say, alright, let's go back to the particle in a box model, and we know that the energy for particle in a box of n is equal to h squared n squared over 8ma squared. That is in your lab 4. It's derived in your lab 4. I also derived it during lab. Please love that. That's really super helpful. We can do a lot with that. So now we're going to do also something we did in lab 4. Is we're going to say what is the what's the energy to go up, right? And that's what's going to take a photon to make it go from here to here, right? To excite it. It's going to take a photon, and that's what this is all about. Okay. So dE then is going to equal h squared n2 minus n1 squared, 8ma squared. Agreed? And we know that E is equal to hc over lambda, because we were asking about lambda. That was the question, lambda. So let's write this in terms of lambda. And this is going to be hc over lambda is equal to h squared n2 squared minus n1 squared, 8ma squared. Okay, so lambda then, I'm going to cancel an h out here too. I'm going to do two things. I'm going to invert and then cancel an h out and bring the c over. That's 3 things. 8cma squared over h n2 squared minus n1 squared. Okay, now I'm ready to go. This is going to be for my particle in a box model. Okay. Now let's go through and make a little key for each of these. C is equal to 3.00 times 10 to the 8th meters per second. M is going to be the mass of the particle that's being excited. What is the mass? What is the particle that's being excited here? It's an electron. 9.109 times 10 to the negative 31 kilograms. A is the width, is the box length. And I haven't done that yet. Haven't calculated that yet. Okay, so let's take this guy here. It's going to be 1, 2, 3. 3 times 135, right? It's 3 double bonds. And then 4, or rather 1, 2. 1, 2 single bonds. So it's 2 times 154 single bonds. This is equal to 405. 254 times 2 is 308. Is that right? Yep. Add these together and it's 713 picometers. Okay, so A is 713 times 10 to the minus 12 meters, right? I reminded myself of pico and nano, because I'm going to have to go to nano later when I'm doing the lambda. For now, pico, I just got rid of the pico here, changed it to meters. A is equal to that. H, 6.626 times 10 to the negative 34 joule seconds. And then N2 minus N1 squared is equal to, looks like the first excited state was 4. 4 squared minus 3 squared is equal to 7. Okay, and the last thing I'm going to do is I'm going to do the units and make sure I got everything right. So, the units of each of these. Let me do that here. Okay, the units are C, but it needs to come out to meters, correct? Meters, because that's what this is. Meters is equal to C, which is meters per second, times M, which is kilograms, times A. And A, we're going to do, A we're doing in meters, so this is, but it's A squared, meters squared, right, over H, which is joules, times seconds. Okay? So a joule, and again, joules, what is a joule? Well, a joule is a unit of energy, and so I oftentimes use this. You've seen me do this in class. Joule is equal to mass is kilograms, and V squared is M squared per second squared. Okay, so meters then ought to be meters, kilograms, meters squared over second squared. And I'm going to put my joules in here, and that's going to be kilograms, meters squared over second squared. Okay, it looks like meters then, looks like these kilograms cross off, these meters squared cross off, those cross off, and boom. Okay, so I've got my units all set up correctly as well. I mean, this is just a safety net, which I do because there's a lot on the line, right? So let's go ahead and calculate this now. It's 8, I'm going to run out of space here, 3 times 10 to the 8th, M, 9.11 times 10 to the negative 31, times A squared, which is 713, times 10 to the negative 12 squared, over 6.626 times 10 to the negative 34, times 7, which doesn't have any units in it. Okay. Hope I'm calculating. Yeah, this is my third time at this because I've messed up the other two videos, and one of them I switched the camera. The camera flipped over in the middle of the video and I didn't even see it, so I had to. Okay, so it's 8. Enter 3e8 times 9.11 e minus 31 times 713 e minus 12. Enter squared times, okay, 6.626 e minus 34 divided by 7 divided by, okay, so this comes out to 2.396 times 10 to the negative 7 meters. Wow. Watch this. Meters, nanometers, 1 times 10 to the 9th. Wow. This comes out to 240, right? 240 nanometers. And that's for the particle in a box model. That's the first part. The second question is, how does this compare if the observed, the experimental, is 240 nanometers? How does it compare? The answer is, it's close. Alright, and then the third question, the final question here for homework problem 16.4 is, and this is a big one, this is a very big one. What does this mean? I want to leave it really general right now. What does this mean? What conclusion can you get from this? Okay, I admit there's a hint in the question stem itself. I'm being more general when I say what does this mean? But I would love for you to be able to answer that together. Actually, let me just leave this answer here. I would love for you to be able to answer that when we get together in class. Okay, thank you for the question. Please keep the request for videos coming.